What I'm going to show or illustrate is a freezing point depression problem. And I'm going to treat it sort of like it's you're doing a lab or something. Let's say you have a test tube, and in that test tube you have 100 grams of water sitting in there, of H2O, pure water. The first thing you want to do is you want to freeze it. So I'm going to stick a thermometer in there, and I am going to cool it down until the water freezes. Now, if I plot that on a graph, where I plot temperature against time, what I'm going to find is that as I'm cooling it, the temperature is going to decrease with time, decrease, and then all of a sudden it's going to flatten out in a plateau. That plateau is indicative of a freezing point. So at that point, attractive forces are starting to bring that liquid together in the form of a solid. There's no longer a change in temperature, and I would call that freezing point. If I did this, I would observe that and say that's the freezing point of water, and it happened to be 0 degrees Celsius. Next, what I would do then, or what I want to do, is I'm going to throw in 2 grams of a solute. Now, a solute is going to dissolve in the solvent, meaning the H2O, and it's going to produce a solution. A solution is always going to freeze at a lower temperature than the pure solvent did by itself. So I want to go through this same process. Now I've got a bunch of solute particles in there. Heat it up, remelt it, and this time I'm going to cool it again. Now what I observe this time is a curve that is lower than the original freezing of the pure. That is, in this case, the solution. And a solution always freezes at a lower temperature. It always boils at a higher temperature than the pure solution. This is why you put antifreeze in your car. This is why they put de-icers. And so in this problem, what I'm looking for is the gram formula mass of the solute. Now it's kind of amazing that you can figure out the molar mass, the mass of all the carbons or whatever and hydrogens all added up together by observing a physical property change. But you can't. What I need to do is now identify this new freezing point for the solution. And I think I'll call it right in there. And now I'm going to measure this difference. And let's say that difference, that change in temperature, turns out to be 1.2 degrees Celsius. All right? So, here's how I'm going to solve for the gram formula mass of the 2 grams of junk that I threw in there that messed up the freezing point of water by 1.2 degrees. The first equation looks like this. Delta T is equal to molality times Kf. Now Kf is a constant that describes the solvent, or the H2O. In this case, the Kf for water is equal to 1.86 degrees Celsius per molal, is how it's written. Okay? So, my change in temperature was 1.2 degrees Celsius. Molality is what I'm going to solve for. The Kf for water is 1.86 degrees Celsius per molal. Okay? So, solving for molality, I will go 1.2 divided by 1.86, and I end up with 0.65. And you would describe that as a molal solution. Molal. All right. The next next equation I'm going to use is that of molality, which is equal to moles of solute. It's a U in there, you can't really see it, over kilograms of solvent. So setting up 0.65 molality that I solved in the first equation, that's going to equal X moles of solute over kilograms of solvent. Now the kilograms of the grams of solvent that I used was 100 grams. That means I have 1 kilogram because there's 1,000 grams per kilogram. So I multiply that by that and I end up with X being equal to 0.065 moles of solute. And this is something that you would expect, I mean, because what's messing up the freezing point is the fact that you have particles interfering with the normal freezing of that solvent. And so the more moles I have, the more it's going to screw up the freezing point. So now once I've got that, once I have 0.065 moles, I figured out how many individual moles are in that solution. I'm going to use this formula for solving gram formula mass from moles. So a mole is equal to the number of grams divided by the GFM. So here I have 0.065 moles being equal to, I put 2 grams in there over the GFM. Solving for the gram formula mass, I'm going to take 2 and divide by 0.065. 2 divided by 0.065 ends up giving me a gram formula mass equal to 30.7 or 31 grams per mole. So it's a way of figuring out what the molar mass is of that solute that resulted in a dropping of the freezing point. Calculations will be exactly the same for boiling point elevation. The only difference is, instead of the freezing point always being lower as a result of the additional solute, boiling point is always going to be higher as a result of the additional solute.